Hello students, I am Manoj Kundare, the Assistant Professor of Electronic Science. Welcome back to our e-learning platform. In previous video, we have seen the OpAmp as an adder or summing amplifier and the OpAmp as a subtractor. The link of the previous video is available in the description box. Please check it. Now, in this video, we are going to see the voltage to current converter by using operational amplifier. We know that the operational amplifier used for many operations like addition, subtraction, integration and differentiation. Also, the operational amplifier are used for the conversion of voltage to current, similarly current to voltage. In this video, we are going to see the details about the voltage to current converter by using the operational amplifier. Let's start our topic. An op-amp is implemented to simply convert the voltage signal to corresponding current signal. The op-amp used for this purpose is IC LM741. That means our normal IC LM741 is used for the voltage to current converter. We already seen the details about the IC741. This op-amp is designed to hold the precise amount of current by applying the voltage which is essential to sustain that current throughout the circuit. That means to the IC741 we can apply voltage at its any terminal, inverting or non-inverting, and at the output side we get its proportional current. Okay, I hope you all understand what is the basic operation of this op-amp. Then there are mainly two types that are explained in detail. First one is floating load voltage to current converter and second one is ground load voltage to current converter. That means we can design the voltage to current converter by using two ways. First one is floating load and second one is grounded load. Let's see. First one is the floating load voltage to current converter. As the name indicates, the load resistor is floating in this converter circuit. That is, the resistor RL is not connected to ground. That means, what is meant by floating load? That means, when the load is not connected to the ground, then it is called as the floating load. Here, in this diagram, we can see RL is the load resistor and it is not connected anywhere to the ground. It is connected in the feedback path. Okay, I hope you all understand this circuit diagram. Let's see once again. If we look at carefully at the diagram, then we can see here that here in this diagram the input supply is given to the non-inverting terminal and the output is connected to the inverting terminal through load RL. Here load RL is not connected to ground, hence it is known as the floating load. I hope you all now understand what is the floating load configuration. Now the voltage V in, which is the input voltage, is given to the non-inverting input terminal like this. The inverting input terminal is driven by the feedback voltage which is across the resistor RL. It is also called as current series negative feedback amplifier. Okay, I hope you all understand the connection diagram. Now let's see the expression for the output. We know that we are giving here voltage input, at the output we get current. For that purpose, first apply Kirchhoff's voltage law to the input loop. We get V in is equal to Vd plus Vf. That means the V in, by using Kirchhoff's voltage law, we can write here the V in is equal to Vd, that means differential voltage, plus the voltage at this point. Hence, but as the open loop gain of this op amp is very large, therefore Vd is equal to 0. We know that the open loop gain of the non-inverting amplifier is very large, therefore Vd is equal to 0. Hence we can write here V in is equal to Vf. We write here V in is equal to Vf due to the virtual ground concept. We learned already that virtual ground concept says the voltage at this Vf point is almost equal to the voltage at this point. Hence, we write here V in is equal to Vf. I hope you all remember the virtual ground concept. But V in is equal to R1 into I0. Here, V in has the value R1 into I0, where I0 is the output current. Okay. Therefore, we can write here I0, that means output current, is equal to V in upon R1. This is our required equation, that is I0 or I0 is equal to V in upon R1. This is the required output current. I hope you all understand this expression. Now, let's see the conclusion about this equation. The above equation indicates that the input voltage V in is converted into proportional to output current. Okay. If R1 is precision resistor, then we can precisely adjust the output current. That is, from this equation we conclude that the output current is proportional to the input voltage. Okay. And if R1 can be precisely maintained, then we can adjust this output current. I hope you all understand this. Let's see once again the expression of the output current. Here at the input loop, if we apply, that means at this loop, if we apply Kirchhoff's voltage law, then we can write that V in is equal to Vd plus Vf, where Vd is the differential voltage and Vf is the voltage obtained from the feedback path. Okay. As the open loop gain of this op amp is very large, hence here Vd is equal to 0. Due to virtual ground concept, we can write that Vf and V in are at the same potential, hence we can write here V in is equal to Vf. Okay. Now let's find the voltage at Vf. Here we can write the voltage at Vf by using R1 into the current I0. But we already seen that Vf is equal to V in, hence instead of Vf we can write here V in is equal to R1 into I0. Okay, that is we write here R1 into I0, where I0 is the output current. If we simplify this equation, then we can write that the output current I0 is equal to V in upon R1. I hope you all understand the output equation. Now let's see the grounded load voltage to current converter. The grounded load means here the load resistor RL is connected to the ground. In this diagram we can see here that the load resistor is RL and it is connected to the ground, hence it is called as the grounded load voltage to current converter. This voltage to current converter is also known as Holland current converter. Here one end of the load is always grounded like this. Okay. Now for the circuit analysis, we have to first determine the voltage V in and then relationship between or the connection between the input voltage and the load current can be achieved. That means we can obtain the expression of the final output by using two ways. The first one is, first of all, we have to determine the voltage V in and then we have to find the relationship between the input voltage V in and the load current. Let's start. Let's get to first step to determine V1, that means to determine the voltage at this point. Okay. Now applying Kirchhoff's current law at V1, we can write that at this point V1 we have to apply the Kirchhoff's current law. and the Kirchhoff's current law says that the current entering junction is always equal to the current leaving the junction. Here, the current entering the junction is I1 and I2. Hence, I1 plus I2 is equal to the current leaving junction IL. Here, the IB is also present, but we know that the input impedance of this op-amp is very high, hence no current flows through the input terminals. Therefore, IB has the value 0. Hence, we can directly write that IL is equal to I1 plus I2. I hope you all understand this equation. But I1 has the value here. I1 has the value V in minus V1 upon R. That means by Ohm's law we know that V is equal to IR. Okay, let's see once again. V is equal to IR and I is equal to V upon R. V is the potential difference between 2 points. Hence for I1 here the R is having value this and V is potential difference between V in minus V1. Okay, I hope you all understand this. Similarly, for I2 we can write that here I2 the resistor is R and it is the difference between V1 minus point V0 or VO. Okay, here the current direction says that in this direction, here the current in this direction, hence we can write here V0 minus V1, okay, upon R. I hope you all understand how we put the value of I1 V in minus V1 upon R and how we put the value I2 is equal to V0 minus V1 upon R. Okay, now let's simplify this. We can write that R is common and goes to other side. We get IL into R and here we require V in plus V0 minus twice V1. That means after simplification of this equation we get V in plus V0 minus twice V1 is equal to ILR. Okay, now rearrange this equation. We get V1 is equal to V in plus V0 minus ILR upon 2. Okay, this is the equation for V1. Now let's go to step second. Try to find the relation between V1 and IL. The op-amp is connected in non-inverting mode. We can see that here the input is given to the non-inverting terminal. Okay, hence the gain of the non-inverting amplifier is 1 plus Rf upon R. We know that the gain of the non-inverting amplifier is equal to 1 plus Rf upon R. But here Rf is equal to R. That means all the resistors have the same value. Hence we get AV is equal to 1 plus 1. That means 2. I hope you all understand this because Rf upon R, that means feedback resistor, and the resistor has the same value. Hence we get here R upon R, that is equal to 2. That means the gain of the non-inverting amplifier is now 2. Hence the output voltage is given by V0 is equal to AVF into V1, that is twice V1. Okay, that means the output voltage is now twice V1 because the gain is having value 2. I hope you all understand this. Now let's substitute V1 is equal to V in plus V0 minus ILR upon 2 in the equation. V0 is equal to twice V1. That means we have to put the value of V1, this value of V1 in this equation. We get V0 or Vout is equal to 2 into value of V1 is V in plus V0 minus ILR upon 2. Then 2 gets cancel. We get V0 is equal to V in plus V0 minus ILR. Then here V0 gets cancelled and we get ILR is equal to V in. Now rearrange this equation, we get IL is equal to V in upon R. This is our required equation, that is the load current is proportional to the input voltage. I hope you all understand this expression in case of the grounded load. Okay. Now let's see the applications of voltage to current converter. The voltage to current converter are used in many applications like diode match finder, Zener diode testing, as a relay driver, as a LED driver or tester, and in DC voltmeter. Okay, I hope you all understand the voltage to current converter in floating mode load and the grounded load resistor. Okay, thank you.